Welcome to topic 8.3, electric fields, daily video number 3. In this video, we will define and graph the behavior of charges and electric fields for conductors and insulators. My name is Eastman Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. Let's start by comparing conductors and insulators. When you look at a conductor, electrons are easily able to move throughout the material. It has a high electric permittivity. In fact, electrons can go so far away, like from this side to some other place on the other side of the Earth, that you might even say that the electric permittivity is infinite. But we don't need to worry about that. Let's instead just say that it has a very high electric permittivity. When in electrostatic equilibrium, though, this is the key idea for conductors, the charges will always reside on the outside surface of the conductor. It doesn't matter if it's solid or if it's hollow. As long as that surface is the conductor, that's where all the charges are existing. And we're not even saying like slightly inside the surface. We're saying like the outer surface of like a piece of foil. It's the outside that has the charge and not the inside. Compared to insulators, those electrons are more tightly bound to their atoms. That's what makes them an insulator. Yes, they can kind of polarize and stretch around a bit, but they're not drifting the same way that electrons might inside of a conductor. Also, whenever we talk about an insulator, we're going to have to give you how the charges are distributed. Yes, we can place them only on the outside. Like we'd have to place them there and they're going to stay there. Or you can kind of imagine that we distribute them all throughout the material in some sort of symmetric way. And then that's how we'd solve that problem. So insulators, wherever we place the charges, that's where they're going to stay forever. They can polarize a little bit versus conductors. They're going to shift where they need to, but ultimately stay on the outside surface of that conductor. So let's talk a little bit about electrostatic equilibrium. When there's no more change in the distribution of charge for a given object, if all the charges are sitting still, we're calling that electrostatic equilibrium. It means that the net force in every single object is essentially zero. So I have all these little force vectors pointing in different directions. And if I sum them all up, if the net force is zero, that means it's not going to accelerate. And if it's not going to accelerate, if it was at rest, it's not going to start moving. Now I can tell you're doubting. You're like, I don't think all those add up to zero. Well, let's see. We're going to drag each one down here, tail to tip, to add them all up. And wouldn't you know it, oh my gosh, those forces did add up to zero. So if you see a system that's an electrostatic equilibrium, this is what we mean. The forces don't have to be the same, but that the sum of all of them is going to add up to right back to where we started. There's no net force. So if we take a conductor and we add some charge to it, it's not going to sit there. Electrons repel each other. They have those electrostatic forces that are repelling each other apart as a bunch of pairs. They're going to move as far apart as they can on the conductor. And in particular, they're going to stay on the surface. So there they go. That's pretty fun and exciting. So if you look at the inside of it, here's another fun fact that conductors on the interior of it are always going to have an electric field that is zero. Always. You're like, well, what if I'm not quite in the center? Well, let's take a look. If you move a little bit over here, these are going to pull a little bit stronger, but then these are going to pull equal, but there's more of them. So on this whole side, there's all these charges pulling to the right, or on this side, there's only two pulling to the left. Even if you don't quite believe it's going to cancel, I can see it in your eyes, right? If you take all these electric fields, sure enough, they add back up to zero again. So anywhere you move inside of a conductor, you are going to have the electric field be zero. Pretty cool. So if we look at the electric fields at the surface of a conductor, they're always going to be applied perpendicularly to that surface. Always. Why? Well, we'll kind of explore that here in just a second, because this looks kind of familiar. Where have we seen something like this before? Oh my gosh, it's the Earth and that gazelle again, right? Here on Earth, when we're really, really close to it, you're going to say, hey, gravity is a constant. It's 9.8 meters per second squared. The same thing's true for a conductor. If you could hang out at this quantum level and just like hang out on the surface of your charge, you would look left and look right, and you would swear that the charge is flat. But it's not. It is curved. You're just so close to the surface that it looks like it's uniform. So we have our conductors. They have spherical symmetry. There's something else we need to look at. If they're all perpendicular at the surface, you can imagine extending those towards the center, and you can actually treat a charged sphere as though it's just a single point charge located at the center of that sphere. Seems interesting, but it is true, because if you're outside of it, this electric field is just the same as a single charge at the middle versus all the charges distributed on the outside. And this is actually a little symmetry that can happen, that if ever you're outside of a conductor, or heck, if you're outside of an insulator, you can treat that whole charged object as just being a single point there in the center. Where, as a fun fact as well, the radius that you measure isn't to the surface of the conductor. The radius is always to the center of the charge. Kind of like what you did in mechanics, where you always measure to the center of mass of the object. For electrostatics, we want to measure to the center of charge of that object. So hooray, make a claim. If you were to sketch a point charge versus a conducting sphere that have the exact same charges, but one has a radius, one's just a single point, what would be different about those graphs? If you want to sketch it out, you can, because that's what we're going to explore here on this next slide. So here we go. A point charge, our sphere. How are they going to be different? Well, that point charge is just going to follow that inverse square law, decaying as a function of radius as we end up moving away, where the sphere, inside of it, the electric field is going to be 0. Because while we're inside a conductor, the electric field is 0. Then it's going to jump back up and kind of decay. Yes, it is discontinuous. There is that gap that ends up happening. But if that bugs you, take a look. This blue line represents what it would have looked like. That's basically this one over here on the left. On this side, it's as though the graph continued, but once we get to the edge, it just jumps up to be behaving like a point charge. Because once we're outside the radius of the conducting sphere, it's going to behave just like a point charge. And sure enough, that point there and that point there are the exact same value. So going back to that previous question, if we're comparing a point charge and a conducting sphere of the same charge, what's different? Only the electric field inside the charges are different. Everything outside is going to be the exact same. You wouldn't even know the difference. If you were far away, you wouldn't be able to tell the difference. So let's look at another example. In particular here, we have some quantitative graphing, right? We have a metal sphere with a radius of 0.2 meters and a surface charge density of 1 microcoulomb per meter squared in electrostatic equilibrium. We need to graph the magnitude of the electric field as a function of the radius. Well, we have the charge density, we have our area. If we put those two things together, we can find the total charge on our sphere. We also have this equation for the electric field of a point charge. And if we sum these things together with Coulomb's constant, we're going to get this setup here. Plugging in for radius, we get this collection of values, where these first few are going to be 0. And once we get outside, or technically right on the radius of that sphere, we jump up to its value, and then it decays downward from there. If we plot these points, we might get something that looks like this. This should look familiar, right? If we're quantitatively graphing, we have our axes that are properly labeled, properly scaled. We have our data values that we've plotted each point clearly where it needs to be, and we get the same kind of trend to occur. If you wanted to connect these with a little kind of trend line, you could, but ultimately, leaving the data just like this is absolutely fine to kind of see how it looks and compares. So let's look at insulators instead. While in electrostatic equilibrium, the excess charge is distributed throughout that object, throughout the sphere, as opposed to just residing on the outside edge, and the electric field may have a non-zero value. So we can put charges all throughout the entire setup, and as a result, when we look at this thing, we're going to see that we can either have uniform charge densities. Let's just say it's all the same thing, which would be this. Rho is the charge density for a volume. Or we can have radial symmetry, which, again, try my best for this one. We're basically saying the density here is the same, and we get going out, it gets either more or less dense radially from the center. So how we solve these, we're going to have to use Gauss's law in a more formal setting in topic 8.5. But right now, just know that we can set up charges either way, to either be uniform or varied, but it's going to stay that way, and the charges don't just exist on the outside. So if we compare these two, we don't necessarily have the knowledge yet what it's going to look like inside, but we're going to expect that outside they're going to look the exact same. In this case, it goes up and goes right back down just like it would have previously. Key thing I want to compare is for an insulating sphere, it's not 0 inside like it was for a conductor. We have some changing value. And just to highlight this, if we have different charge density distributions, we're not always going to get a linear setup there. It can be all different fun shapes that happen in between. But once we go outside of it, it once again just gets treated like a point charge, and everything's good from there, kind of comparing these two setups. So what should we take away from this video? A couple things, mainly that insulators and conductors behave differently, and that the electric field inside of any conductor is 0. That is just a fact to know and just have it in your brain, is that any conductor, and you're like, hey, what's the electric field in there? 0. If it's an electrostatic equilibrium. So the excess charge on any conductor always exists on the outside surface of that conductor when it's in electrostatic equilibrium, and the electric field inside of an insulator can change and be different, and we're going to learn more about that in a future topic video. This is the end of Unit 8.3, and I look forward to seeing you in Unit 8.4. Thanks so much.